Hello, Pathways class. It is Monday, and we are going to talk about the electromagnetic spectrum today. But really, a couple things I wanted to talk about was one, you should have by now completed talking about two of these parts of the electromagnetic spectrum and writing them up and sharing them with me. We're going to focus today on right in the middle of this visible light, which we call white light, which is really a combination of all these colors. When you combine red, orange, yellow, green, blue, indigo, and violet, you get white light. Like the light is hitting me off my lights in here, lights coming from the sun. That is white light. It's actually a combination of all these lights. And you can split that white light up. If you've ever seen a rainbow, that's when the light from the sun is hitting a raindrop or an ice crystal, and it acts like a prism. And a prism is something that is designed to split the light, and it splits it up into its original wavelengths. And if you look here, red is the closest one to the right, which means that has the largest wavelength. And as you go towards the left here, the wavelength gets shorter and shorter. So we go from red to violet on this side, and that's Roy G. Biv: red, orange, yellow, blue, indigo, and violet. You'll notice these colors are very similar down here, that indigo and violet, but there is a difference. You're getting a shorter wavelength and the color changes. After that, we can't see those colors. If you were a bee, you could start to see in these colors over here. You start to see ultraviolet rays. We can't see them. Our eyes are only designed to see these colors. And that's what we're going to talk about today, is the human eye and how it works. How do we see these colors? And we're going to take a quick tour through the eye here, and we'll go through. So here's a pretty simple structure of the eye. And this is your eyeball, let's say here. And the pupil is going to this area right here. It's basically the space. That would be this black spot right here. This is the pupil. And this isn't really so much a structure, but a space. Your eye, looking at where to go, structure of the eye. This space right here, this is the pupil, and it's black. This is actually a space. It's a hole. If this cornea wasn't here, this cornea is a protective covering. If this cornea wasn't here, you could take something and put it right through the eye and touch the lens. You wouldn't want to do that, but this here is actually a hole. So you could take an object and just put it right through that hole. You'd hit the lens, but if you went right through the lens, then you would just be in this space right here. So that pupil is actually a hole that goes through. Cornea is this protective covering. The iris is the colored part of your eye, and that's actually muscle. And what that iris's job is to do is to act like a filter. Which way should I put this? And as it constricts, okay, or comes in on all sides, it reduces the amount of light that could come in. If it's really bright outside, that pupil will constrict so that very little light comes through. If you've ever been out in the sun, you've been in the dark, maybe in a movie theater, and then come out and you're like, oh, it's too much light. Because in the movie theater where it was dark, that iris had expanded this way and relaxed, making the hole bigger, allowing more light to come through. As you hit the light, they quickly contract, but not quick enough, because a lot of light goes in and it hurts your eyes right away. So what we're looking at here is this iris here, is this colored part, and this expands and contracts, making this hole larger or smaller to let more light in. You can see even in these different pictures, this is what the iris looks like when it's contracted. This area must be darker. Here, this area must be lighter because it has filtered in, come all the way in to get as little light in as possible. Okay? And if you look really closely at it, this is what it really looks like. And here's a slow motion video of the iris contracting. Now, this person's eye was in the dark, so it's pretty, the iris is opened up. Then they expose, there it is, Oh, there it is, and then contracts when the light is on it. You can see it contracting, making it smaller, covering up this hole so that less light comes in. Okay, so let's go back to our structure here. Now the lens is important. The lens is what focuses, just like you would have on a camera or a projector. The lens focuses the light. The lens is a convex lens, which means it's thicker in the center and shorter, thinner on the edges. And that's important because that does is it takes the light that is up here and it bends it down. And this light here, and bends it up. It bends it all to one focal point. So all this light is being collected to one spot. You're trying to get as much light as possible. That's why in the dark it's so hard to see. You might be really concentrating because there's not enough light coming in. Or if there's too much light coming in, that iris is as small as possible, all that light that's there in that sun is being pulled down. You might have to shade your eyes or put a hat on, or you squint even more to get less of the light coming in. But that's good for bending the light. But what is not good for your eye is what a convex lens does. What a convex lens does, though, is it flips the image upside down. You can try this if you have a magnifying glass at home. A magnifying glass is a convex lens. Take a magnifying glass, put it up to some newspaper or something with print or an image, and as you look at it, the image will be upside down. And that's because that's what happens. This will continue to flip. This light from here will go all the way down to that way. And the problem with that for you is everything on the inside of your eye, all that light, everything you look at is upside down on your eye. And we'll have to talk about what happens, how you actually see things. But when the light comes in, it hits that lens and it bends it and it flips the image upside down. And it's projected onto this retina here. When that light from her shoes hits the retina and her head hits that, it activates some cells called rods and cones. Let me find my rods and cones. No. There they are. So there's these rods and cones on the back of your retina right here. It's all this area here. And you can kind of think of that as like a movie screen, like a sensitive one. As the light hits it, so here's an image here. Here's the girl, and her head is here, and that light comes in, but then it's reflected down this way, and it activates these rods and cones. The cones detect color. The rods detect blacks and whites and grays. So if someone is colorblind, one of the reasons they might be colorblind is because they have trouble with these cones. They're not picking up certain colors of light. Remember that electromagnetic spectrum has all these colors. So if your rods are fine, but your cones that pick up red don't work, you'll be colorblind to the color red. If the cones that pick up the colors, green through blues, then you won't see those colors. I knew a guy one time, he wore red, he bought red things because that was basically the only color he could see. Everything from about here down, all those cones didn't work. He could only see the color red. Everything else was a grayish color, and he saw red. So he liked to buy things that were red and wear things that were red because he could see those colors. So your rods and cones are here. When those get activated, they send a signal right here to this optic nerve, right down through here. And actually, you can see there's a little spot where there's no rods and cones. This is a blind spot. You actually have a little blind spot here where this optic nerve comes in, where there's no rods and cones. And some would say, well, I didn't see that. And one of the reasons they may not have seen it for a split second was because maybe something was in their blind spot. It could be because it was off to the side, the peripheral vision, because we don't really see things really well from the side because light isn't going through that hole, that pupil there. It's when it's coming in this way is better. So these rods and cones get activated, and the signal goes from your optic nerve to your brain. And let me pull up a picture right here of optic nerves to brain. Okay, and What's interesting is that your left eye sends the signal to the right part of your brain, and your right eye sends a signal to the left part of your brain. Let's see if we can find that picture here. Of course, got all kind of stuff besides what I wanted. Where'd that image go? We'll just go back a second here. Okay, here's a good picture. Just blow it up. So this left eye is hooked up to the right side of your brain, and this right eye is hooked up to the left side of your brain. And that's where the signal is sent. So what I'm going to say now is you do not see with these eyes. These eyes send a message, an electrical message, based on the activation of these rods and cones, send a message to this optic nerve, which sends a message to your brain. The right eye sends it to the left, and the left eye sends it to the right. But remember what we said earlier, that image is also upside down. So your brain very quickly does some amazing things. It takes the image from your right eye that goes here and your left eye that's there, and it combines those images into a three-dimensional image. Because your brain has learned through depth perception that we don't live in a flat 2D world. So it combines those two images to make a 3D image. But then it also makes some very, very fast assumptions. So if your brain was looking at this girl, which your brain is, it knows that people do not walk around upside down, which it is here. So what your brain actually does is it takes that image of that person upside down and it flips it right side up in your brain. Whenever you're looking at something, that image is actually upside down on your eyeball right here. But that signal is sent to your brain, and your brain says, well, that's not possible. Trees don't grow that way. And so your brain flips the image what it believes is the correct way. And that's how our brains get fooled sometimes. That's how a lot of optical illusions work. Your brain is being tricked by the signal it is getting from light bouncing off of things. That's why sometimes with a eyewitness account, you can have 10 different witnesses giving 6, 7, 8, maybe even more descriptions of a person. How tall they were, what color shirt was on, what color hat they had on, whether they had a beard or not. Because they have what's going on in their brain, and it was a stressful situation. Maybe there was a robbery, and they see someone running out, and in their brain, maybe the coat reminded them of a coat that their husband had or their brother, and they're thinking of that coat, so that's what they see. Maybe the person reminded them of someone else quickly, and that image gets imprinted on the image that they thought they saw. So eyewitness accounts can be very misleading. I want to show you one of the most powerful illusions, I think, to demonstrate how your mind gets tricked. And this is what's called a hollow head illusion. This is a mask. This is a mask of a old movie star called Charlie Chaplin. And you have to forgive me, my full screen stuff isn't working too well. It's going to cut out. So I'm going to do this. And what this mask is, it's an old mask, and it's hollow on the one side, so you could put your face in it if you wanted to. It's an old mask. Before latex and rubber were cheaper, everyone had plastic masks like this. And it's put on this rod, and what's going to happen is it's going to rotate around. And your brain is seeing this right now. And it knows, yes, eyes, nose, this is the face, this is the guy's hat, he's got black hair. I've seen this before, and your brain starts filling in all the gaps. This is a mustache, oh, it kind of reminds me of Hitler, but this is something else. So your brain is looking at this going, lips, ears, yep, I've seen all this before. But what happens is, as the mask starts to turn around, you'll start to see on the inside of the mask, so what is pushed in. But your brain will refuse to see that. It knows that faces are not pushed in. As it's walked around for the last 13, 14 years, 15, 16 years you've been alive, faces are not pushed in. Noses pop out, lips pop out, So it will refuse to see it pushed in. What your brain will do is it'll pop the face out. So instead of being pushed in, it will make it look normal and pop it out. Then when the head starts to turn some more and you see the edge again, you'll start to realize it's an edge, it's a mask, and it'll start to go back in. Your brain will make it. So there's no camera tricks here. This is what it is. It is your brain being fooled. Now, I know this is going to happen. I've seen this hundreds of times, but I cannot not see it this way because the version of a human face is so imprinted on my brain that my brain will see it that way. All right, let's take a look at the hollow head. Oh, also, one more thing. It may also even look like it changes direction, like it's rotating one way, and it may start to look like it's rotating the opposite way. Probably will. And it's not rotating the opposite way. Okay. Here comes the head. All right. Now concentrate right in the middle. And there it was. Pretty cool. All right, so if you want to check out show something, that is the Charlie Chaplin hollow head optical illusion. There's lots of versions of this hollow head. I think this is probably the most powerful. So you do not see with your eyes. They are yet just a messenger to send those light waves that activate the retina, send a signal to the optic nerve, to your brain, and your brain interprets those signals. And the way you interpret it, then that's what you see. I want to quickly talk about some different eye problems you might have. One problem you have, you wear glasses or contacts, you can't see really well, is this lens, which is supposed to focus things, doesn't. The lens is not correct. Maybe there's something cloudy on it, like a glaucoma, or maybe it's scratched, or maybe it's just misshapen. There's these ligaments right here and these muscles, and what they do is to focus on things either closer or farther away, they will stretch that lens a little bit, stretch it. And if they don't work, you're not going to see things in focus, just like if you took a lens and focused it. Or over time, like me, most people over time, after 40 years of this lens being stretched out, relax, stretch, relax, stretch, relax, and these muscles and ligaments working, things start to break down. And you'll notice a lot of older people wearing glasses. And that's part of the reason. It's just wear and tear on your eyes. Another thing that might be an issue is something with your optic nerve, something with your retina, not collecting the rods or cones. Another issue might be, and this is a pretty common one, is the shape of the eyeball. And this is common for nearsighted and farsighted. If you have a normal vision, a faraway object is clear, and you have almost a spherical shape. But this is myopia. This is when the eyeball is a little too scrunched down. And what that does is it changes. You notice this focal point is going to be in the wrong spot. It's here as opposed to here. So faraway objects get blurry. Then you can put a lens on that, like eyeglasses or a contact, and it'll change that focal point back on the retina where it should be. The other option is, instead of your eyeball being too squished, it could be too oblong, which means the focal point would be too far back that way, which means you can see far away objects, but you can't see near objects. Then you'd get a different lens, and they would correct it. That's why if you go to the optometrist or the eye doctor, and they put those different lenses in front of you, they can determine A lot of the problems are eyeball related, or they could be lens related, and they'll give you a lens that will adjust that focal point to correct your vision. Okay. If you want to try this, you can. You need a mirror and some light. You can go someplace dark, like in a bathroom if it's dark, or cover up your eyes, get really close to the mirror, and then turn on the light, and you'll see your iris contract really quickly. You can see it expand. It just takes a while. Takes really slowly, but the contraction is really fast. Go someplace where it's really dark. I'll just shut off really dark, not like this, but if it was much darker, get really close to a mirror, and then turn on the lights, and you'll see that iris contract. It's kind of fun. You can do it with someone else too. Both of you sit in the dark, and then flip on the lights, and then look at each other's eyes, gazing. Okay. All right. Well, that was a quick tour of the eye. Hope you enjoyed it, and electromagnetic spectrum. Tomorrow, we're going to talk about longitudinal waves and sound waves. There's your brain. And how sound wave works. And then we're going to talk about how your ear works as well. Okay? All right. That's it for today. Hope you enjoyed our little lesson on how the eye works. And I'll see you tomorrow.